Hello students. In the previous video, we saw about SVM, support vector machine, in particular maximum margin linear separators. So we saw how we calculate the distance from the hyperplane to a support vector, and that value, when you multiply it with 2, you get your margin space or margin size. So for an optimal separable hyperplane, the margin size should be maximum. In today's lecture, we shall solve a numerical on finding or determining the optimal hyperplane. So here goes the question. The question states, find the optimal hyperplane for the set of data points. Data points are given to you. There are 8 data points: 1, 1, 2, 1, 1, -1, 2, -1, 4.0, 5, 1, 5, -1, and 6, 0. And there are 2 classes considered where these 4 data points have been placed in both these classes, class 1 and class 2. Now let's move on to the solution. The first thing that you are going to do is, these 8 data points, you will be plotting it to the 2 classes as shown below. So you can see over here all the 8 data points have been plotted, and we see over here, once you have plotted the data points, you can see that here this is the best possible region where we can have an optimal hyperplane. But we don't know whether this is the exact region that we are looking for. So what is the next step is, we will be considering the data points which are very close to this particular region. So we consider support vector S1, S2 belonging to a particular class, say class 1, and S3 belonging to class 2. As we all know that these support vectors which are nearest to the hyperplane, they help us in calculating the margin space. So we consider only these 3 points, S1, S2 and S3. So the value of S1 is 2, 1, S2 2 minus 1, and S3 4, 0. Now these vectors, they are augmented with a value 1, which is acting as a bias to the input. So simply 2, 1, we will be adding a bias. So S1 becomes S1 dash, which is nothing but 2, 1, 1. Similarly, S2, which is 2 minus 1, now becomes 2 minus 1, 1, because we are adding a bias with a value 1 into this vector. The same goes for S3, which is 4, 0 and 1. Now if you see the graph over here, the plot, we can consider these 2 points to be negative and this side to be positive. So what it has been done? We need to find the parameters alpha 1, alpha 2, alpha 3 based on the following 3 equations. So we consider S1 and S2 to fall on the negative class and S3 to be the positive class. So simply what we will be doing is, we are going to consider the dashes, that is, the inputs that we have augmented with 1, which is your bias. So here it will be alpha 1, alpha 2, alpha 3, and each of these will be multiplied with S1 dash multiplied with S1 dash plus this is alpha 2. This is going to be S2 dash multiplied with S1 dash, alpha 3 multiplied with S3 dash into S1 dash. It's very simple. You will have 1 1, 2 2 and 3 3 diagonally. And here you will be having, this is 1 1 which is 11. Here you will be having 12 and 13. 2 2, so this is 21 and 23. And here it is 3 3, so it is 3 1 and 3 2. We know all these values, so simply we are going to substitute the values in place of S1 dash, S2 dash and S3 dash. And we have equated S1 and S2 to -1 and S3 to your +1. Now we will simply multiply these vectors and get equations. So 2 into 2 is 4 plus 1 into 1 is 1 plus 1 into 1 is 1. So 4 plus 1 which is 6. So it is 6 alpha 1 if you see over here. In a similar manner, you will be finding it for the second term and third term, and in the same fashion for the second and third equation. Now, you can give this as an input in your scientific calculator and solve these three equations simultaneously and find out the values of alpha 1, alpha 2 and alpha 3. On simplification, we get alpha 1 and alpha 2 values as minus 3.25 and alpha 3 is 3.5. The hyperplane that discriminates the positive class, that is your S3, from the negative class is given by, it is nothing but W dash is equal to summation I equal to 1 AI into your SI dash. So simply we will be substituting alpha 1, alpha 2 and alpha 3 values with your S1 dash, S2 dash and S3 dash, and we will be getting W dash. So on substituting, we get the answer, the vector W dash to be 1, 0 and -3. Now as we all know, this last element was the bias. So basically, the separating hyperplane equation y is equal to wx plus b contains w to be only 1 and 0. And b which is there, which is nothing but your offset or the bias, is your -3. If you bring the 3 to the left hand side, it is nothing but b plus 3 is equal to 0. Students, keep one point in mind. When w is equal to 1, 0, you always draw the hyperplane, the optimal hyperplane perpendicular to your x-axis. So here it is w10. So you draw the hyperplane perpendicular to your x-axis or parallel to your y-axis. If suppose if it would have been 0, 1, then you would have drawn the hyperplane parallel to x1 and perpendicular to x2. So keep this point in mind. And b equal to -3, when we bring b to the other side, it is b plus 3. and that is why we have considered a line that is passing perpendicular to x1 and parallel to x2 to be the optimum hyperplane, that is segregating the two classes, class 1 and class 2. Thank you.